So contradiction is one of the more classic proof types. Um, it is also possibly one of the more confusing ones. So how we do a proof by contradiction is we start by looking at our statement, which in this case is to prove that the square root of 2 is irrational. How you start a contradiction is you actually assume the opposite is true. So how we're going to work this is we're going to say assume the square root of 2 is indeed rational. So it asks us to prove that it's irrational, but we're going to start by assuming that it is, and then try prove that it can't possibly be rational, so it is therefore irrational. It's a very confusing thing to get. A lot of people often memorize this proof, but I feel like I can't do it justice unless I properly describe how it works. So in a way, we're trying to end up with a double negative. So we're assuming that it's rational. We show that it cannot possibly be rational. It is therefore irrational. So how we're going to work this is we're going to say let the square root of 2 equal some rational function a over b, where a and b firstly are positive integers, but also a is not some multiple of b, where the multiplicator or the scaling factor is also an integer. Positive integer, that is. So we're having this be in its simplest form of some fraction. Therefore, we can say that 2, if we square both sides, is a squared over b squared, which would therefore imply that a squared is 2 times b squared. We can then infer that a must be even, since a squared is some number times 2, which will be an even number. And for most practical purposes, if a squared is even, that means a is even for a's that do actually have a nice square root. Cool. So we've deduced one thing. So if a is even, that directly implies that a is equal to 2 times k. Actually, no, I'll use a different letter. So 2 times c, where again, c is a positive number and cannot possibly be a multiple of each. It is a multiple of a because we're transforming a, but it can't be, say, a multiple of b. But we're going to show that it is. So again, we'll plop a is equal to 2c. So 2c goes in there, and we get 4c squared is 2b squared. Divided by 2, we can show that b squared is 2 times c squared. So we've now shown that b must be even, for the same reason as above. Therefore, if a is even and b is even, so if a and b are both even, they share a common factor of 2, which contradicts the initial setup. Therefore, root 2 is not rational. That's a poorly drawn rational key. We'll try that again. Is not rational. QED, and the proof is over. So this can be shown for all numbers which do have, which are not perfect squares. Try show it for the square root of 3. It follows the same steps. Now the square root of 4, although it may appear that the steps are the same, you actually run into a double contradiction, which is a double negative, a double negative. So it's a bit weird, but pretty much any number that isn't a perfect square, if you take the square root of it, it is clearly not rational. And that is the archetypal proof by contradiction.